Welcome to Joey's Tech, my friends. In this video, I am going to teach you the quicksort algorithm. Apart from telling you how the quicksort algorithm works, I'll be telling you how to construct the quicksort algorithm and its time complexity. So I don't want you to miss any part of this video. Therefore, make sure you watch this video completely till the end. Quicksort algorithm is a divide and conquer algorithm that chooses an element as a pivot and partitions the given array around the chosen pivot element. This is the array that we are going to sort using the quicksort algorithm. The key thing in a quicksort algorithm is picking the pivot. There are many ways using which you can choose the pivot. You can pick the first element of the array as the pivot, or you can pick the last element of the array as the pivot, or you can pick any random element as the pivot, or you can simply pick the median element as the pivot. Choosing the way to pick up the pivot element gives rise to different versions of quicksort algorithm, but the procedure stays the same. In this video, I will choose the last element of the array as the pivot. Let's begin understanding the algorithm now. Like I said, I am going to choose the last element of the array as the pivot. So 70 is the pivot for me. Now what we are going to do, we are going to put all the smaller elements than 70 on its left and all the greater elements than 70 on its right. Let's see how we do it. We define an index variable I that is going to run from 0, which is the first element of the array, till this element that is previous to the pivot element. So I will be 0, and at the same time we are going to declare and initialize another variable j to -1. So this will be its correct position. In a while you will understand what's going on. So the execution begins now. So the element at I, which is 10, will be compared against the pivot element, which is 70. Is 10 less than 70? Yes. So what's going to happen? The algo will increment j by 1, which will now become 0. Alright. And we exchange the element at I with the element at index j. Now in this case, they happen to point to the same element. So even the exchange takes place, it is not going to produce any impact and the array will stay the same. Big picture is we kept 10, which is less than 70, on the left side of 70. Okay. Now I starts pointing to this index 1, which has 80 as the element, while j continues to point to 0 as of now. Now 80 will be compared against the pivot element. So is 80 less than 70? No. So nothing happens. No exchange takes place. We don't want to put any number greater than pivot on its left. Okay. Now I will point to index 2, which has 30 as the element. Now 30 is smaller than the pivot element, which is 70. So now the swap will happen. But before that, we will increment j. So it starts pointing to index 1, because here is where 30 will be placed and 80 will be placed at index 2, which is the current value of I. Okay. A simple swap has happened. See, now we have two elements less than 70 on the left hand side. Now I will move one step further and will point to 3. We have 90 as the value over here. 90 will be compared against 70. Is 90 less than 70? No. So nothing happens. No exchange takes place. J doesn't move in this case. Okay, it stays here and continues to point to 1. Now I moves one step further and it points to index 4. What's the value here? 40. 40 gets compared against the pivot element, which is 70. Is 40 less than 70? Yes. So in this case, a swap needs to happen. So what is going to happen? J will increment by 1 and will start pointing to 2, the index 2. So here what will happen? 40 will be placed over here and 80 will be placed over here in the slot pointed by index 4. So now you understand what j is doing. It tells you the index of the slot where you need to put the next element, which is less than 70, which is the pivot element. Now I moves by one step and it starts pointing to this index 5. It has the value 5. What's the element here? 50. 50 gets compared against 70. Is 50 less than 70? Yes. So now the swap has to happen. We have got another element that is less than the pivot element and it needs to be placed at its right position. So what will be its right position? It will be determined by this variable j. We need to increment j by 1. So it will start pointing to this index 3. That means 50 will be exchanged with 90. Let's do the swap. So 50 will be placed here and 90 will be placed here. Okay. Now you see 4 elements less than the pivot element are on the left. Alright. Now in the next iteration, I will move one step further and it will point to 6. It was supposed to run till here, till this cell. Hence the algorithm is going to come out of the loop. And now the final thing that we do in this round of execution is we put the pivot element at its proper place, right? Because we want the smaller elements than the pivot to exist on its left and the greater elements to be placed on its right. So the algorithm will place the pivot element at j plus 1. What is j plus 1? This cell, index 4. So let's place 70 over here and the element at this index, which is 80, will be placed over here. So let's do the exchange. So it will be 70 over here and 80 over here. Okay. Now it completely makes sense, right? Why we placed it at j plus 1? See, now everything looks just fine. All the elements smaller than 70 are before it, are on its left, and all the elements greater than 70 are on its right. This is basically the partition algorithm that runs within the quicksort algorithm. Now let me tell you that quicksort is a recursive algorithm. So the array now will be broken into 2 halves at 70. We are going to get a left array which will be this and a right array which will be this. Let's look at the left array now, which contains 10, 30, 40 and 50. Now since we are choosing the last element as the pivot, so we'll choose 50 as the pivot element and apply the same partition algorithm that we applied just now on the main array with 50 as the pivot element. And you can see this array is already sorted in the correct order. So no change will happen to this array. Alright. Now this array will further get broken into 2 arrays around 50. So the left array will contain 10, 30 and 40 and the right array will contain nothing, as there is nothing on the right hand side of 50. Alright. Now 40 becomes the pivot here in this array and the partition algorithm will now be applied to this array, keeping 40 as the pivot element. The array is already sorted, you can see. So no change will occur to this array. No change will be done by the partition algorithm to this array. The division of this array, the further division of this array will now happen around 40. So 10 and 30 will go into the newly divided left array. And since there is nothing on the right hand side of 40, so the right array will be empty. Now we have reached the final level of this branch of the recursion tree. In this array, 30 will be the pivot element and there is nothing but 10 on its left. So when the partition algorithm will be applied, this array will stay the same, no change will occur. Partition will then happen around 30 now, and after division 10 will remain in the left array and nothing will be there in the right array since there is no element after 30. At this level, the algorithm will stop from proceeding further, from dividing further on the left, because it has got size 1 element now. It has reached the atomic unit. Now the algorithm will come here and find that there is no element here. So it will go up to this level and target this portion. Okay. Here the algorithm will hit this partition of the array, which again doesn't have any element. So the algorithm will go up further to this recursion level. At this level, the right array also doesn't have any element. So there is nothing to sort, nothing to process over here. So now the algorithm is going to move up one level further and is going to come to this recursion level. Here the algorithm is going to find elements in the right array. We have 90 and 80 here. 80 is going to be the pivot element here, and when the partition algorithm will be applied to this particular array, this array will be sorted like this. Now 80 is the pivot element, so the division will happen around 80. So the left array will now contain nothing. The algo will go here and find nothing, so it's going to come here and find the 90. The array size here is 1, so no partition algorithm will be applied and no further division will happen. And here is where the quicksort algorithm is going to stop. It has finished its job, and thus it is going to get a sorted array like this. This is how the sorting happened using the quicksort algorithm. Let's now develop the quicksort algorithm. More or less what I'm writing is a Java program of the quicksort algorithm. So in the main function, let me first declare and initialize an array. So it will be int square brackets arr, which is going to be the name of the array. It will be 10, 80, 30, 90, 40, 50, 70. Okay, the first line of code we are going to write is the function call to the quicksort function. So let me write quicksort over here. The first parameter of this function will be the array, so it will be arr. The second parameter is going to be the index of the first element of the array, which is obviously going to be 0. And the third parameter will be the index of the last element of the array, because we are passing the whole array. So it will be arr dot length -1. Alright, now let's create the quicksort function. So it will be static void quicksort. Obviously it's going to receive an array, so it will be int square brackets arr, and then the second parameter will be a variable low, and the third parameter, the final parameter, will be a variable high. Alright, very much self-explanatory, but let me tell you that the first parameter will be the array, second parameter will be the starting index represented by the variable low, third parameter will be the last index represented by the variable high. Now within the body of the quicksort function, we'll first write the condition that will stop the recursion from going further. Remember, when we reached the atomic units, further division won't happen, recursion won't proceed further. So we'll have to write the condition to stop it. So you see, the recursion should stop after these atomic units are encountered, or if there are no elements in the array. So the condition will be if low is less than high. Alright, if this condition is breached, the recursion will stop. No further division will happen. If you see here, low is not going to be less than high, so this condition will be false here. Here this condition will fail as well. Here also this condition will fail as well, so the recursion will stop. Now once any of these arrays is presented to the algorithm, the partition function should be called. The partition algorithm has to be applied on each of these arrays. Alright, so within the if block, we are going to make a function call to the partition function. So it will be partition, and within brackets, the first parameter will be array itself. The second parameter will be the low variable, and the third parameter will be high. Okay, basically low and high are the starting and the ending index. Now this partition function is going to return the index of the pivot element. So we are going to receive it in a variable known as pi. So it will be int pi equals to partition function call. Alright, we'll come to partition function in a while. Now we'll make recursive calls to the quicksort function, because that's what is happening over here. So one recursive call will happen for this array, that means the left division, and one recursive call will happen for the right division. So it will be quicksort. The first parameter will be array. The second parameter is going to be low, that's the starting index, but the ending index this time will be pi -1. Okay, So it is very much self-explanatory. The second parameter is going to be the starting index, and the last index will be 1 before the index of the pivot element. All right. And the next function call will be quicksort. Array will be passed again as the first parameter, but this time the starting index will be pi plus 1 and the ending index will be high. Okay. Here also the starting index will be the index of the element 1 after the pivot element, and high will represent the index of the last element of the array. So after the partition algorithm is applied over here and the first division happens, the first recursive call will have the value of low variable as 0. All right. And the ending index will be 3, which is 1 less than 4, which is the index of the pivot element. So pi minus 1 will be 3. All right. And the second recursive call will have the low index as 5, which is 1 more than the index of the pivot element. And the ending index as 6, which is the index of the last element. Okay, this is it. This is where the quicksort function ends. Now we'll develop the partition function. So it will be static int because it's going to return an index. Partition within brackets, the parameters are very clear. So it will be int array, int low, int high. Okay. First thing what we do inside the partition function, we hunt down the pivot element. So we declare a piv variable. Okay. And what we are going to assign to it? It will be the element at index high. All right. Correct. Because we are interested in making the last element of the array as pivot. Now we are going to declare and initialize the variable j. So it will be int j. What we are going to initialize it to. When we applied the partition algorithm over here, it started from -1. It represented -1 initially. So it was the first element that is represented by low -1. So it will be low -1 over here. Okay. And now the loop will start. So let me write the for loop here. It will be the variable I, which is going to start from low, obviously, and it will run till the element 1 less than the pivot element. All right. So it will be I less than high, or I equals to high -1. Let's make it like this, I plus plus. Okay. Now within this for loop, we'll compare the element represented by I with the pivot element. So let's write the code for it. So it will be if arr within square brackets I less than piv. Okay. Now if the element represented by I is less than the pivot, then we increment j here, because now we'll be swapping the element represented by I with the element represented by j. So it will be j increment operator, and then we are going to write a call to the swap function. So it will be swap the array. It will be I and j. Now let me quickly write the swap function. There you go. I have quickly written the swap function. Now after the for loop gets over, we need to place the pivot element at its right place, and its right place will be represented by j plus 1, right? So we call the swap function again. We pass the array, but this time its parameters will be j plus 1. Okay. Here is where the pivot element will be placed, and the element represented by this index will be placed in the last cell of the array where the pivot element currently is, which is represented by high. And finally, this partition function will return the index of the pivot element. Hence, the partition function will return j plus 1. Okay. And that's it. We have just built the Java program implementing the quicksort algorithm. Let me write the code quickly to print the array over here and run it and check if it works. Okay, I have quickly written the code to print the array. Now let's run the program, the quicksort program. There you go. The array is sorted. The program works. We have just sorted the array using the quicksort algorithm. Alright, speaking of the time complexity of the quicksort algorithm, the best case time complexity of the quicksort algorithm is big O n log n, and the worst case time complexity of the quicksort algorithm is big O squared. And with this, we have come to the end of this video. I hope you enjoyed learning the quicksort algorithm from Joey's Tech. I have made videos on other sorting algorithms as well. Please check them out. I'll see you in the next video of Joey's Tech, and only for this video. Goodbye and take very good care of yourself.